Okay, today we are going to do a little bit more with data visualization in in Python, and we will look at Seaborn. So on Wednesday, we introduced Matplotlib, and that's fine. Um, I think Seaborn um, does a lot of stuff that makes it a little bit easier and prettier to kind of quickly do some visual exploration. It's strictly a visual exploration tool, not so much used for kind of heavy statistical analysis. If you need to like deep dive and do things like that, not really the tool for that. But if you just wanted to kind of explore trends and relationships and do exploration of your data, Seaborn is pretty good for that. Um, Depending on what you have, you might need to, let me restart my kernel. You might need to update your Seaborn, otherwise you might get a whole bunch of like warnings. And so you can do SNS. So here I have 13.2. This is so the convention is, NumPy is NP, pandas is PD, matplotlib.pyplot as PLT, and Seaborn as SNS. And once you import Seaborn, you can ask Seaborn dot under double underscore version and see what it says. Okay, you can if you need to update, you can just look up Seaborn Python, and that will be right here, seaborn.pydata.org. You go to installing, and then to update with Conda or install with Conda, you can do Conda install Seaborn. One thing is that the main Anaconda repository, it says, can be slow to add new releases. So you might have to do Conda Forge, and that will be done using Conda install Seaborn -C Conda Forge, Conda-Forge. And that will probably get you the latest version of Seaborn if you need it. Okay. Anyway, let's go ahead and take a look. We are going to look at this Penguins data set. It's a data set that that comes with the Seaborn package, and we can load it up by doing sns.load dataset penguins. And if you go into take a look, you have these different species of penguins, and they come from different islands, and they have different measurements: bill length, bill depth, flipper length, body mass, and the sex of the penguin. Okay, and I think let me see. Data set. Name the data. The penguins. So we have this is kind of the full penguins, and you can look up like Adelie penguins. This is what they look like. And then we have all right, so that's one of the species of penguin. And then you have the chinstrap penguin. Okay, yeah, see they got this little stripe, their chin strap. And then we have the Gentoo penguin, or Gentoo, I don't know how to pronounce that. And they look like this. Okay, so we have these different penguin species, and they're on different islands. I don't know. You can Torgerson Island, and they're all these kind of let's see, you know, they all live in Antarctica, so they're down here. um and I don't know, so this is kind of the data set, and then you have bill length and bill depth. I think is all actually called Coleman length and Coleman depth. So anyway, you have these different measurements, and they come from this thing, and we can just do some visual exploration here. All right, so kind of the most basic is going to be the distribution plot. Okay, so you'll do seaborn.distribution plot data. Here we're going to go from the penguins, and then we'll just do the X variable that we want to do will be flipper length underscore mm. So you just put in the name of your column name. Seaborn runs on Matplotlib. And so after you call Seaborn on this to show your PyPlot, you'll just do plt.show. And this is what the distribution plot looks like. Okay, so basically like a histogram. And that's what that is. Okay, you can add a few arguments here. So let me just come back. So we'll look at seaborn.displot. Okay, seaborn.displot, this is our distribution plot. And you have all of these optional arguments. Let me zoom in a little bit. And so you can add, I don't know, whatever, different things that you want to do. You can add any of these kinds of things, rugs and KDEs. And so here I'm going to set rug equal to true. I'm going to specify bins equal to 20. And so now I'll get 20 bins. And then this down here, this is my rug plot. And this kind of indicates how many little observations did I see. Rug plots work best when you have a continuous distribution. And here, flipper length was measured to the nearest millimeter, which is, you know, about as good as we could hope for. But, you know, you do get kind of these little lines equally spaced out here. Okay, so that's what we have. So this is our rug plot. Okay, you can also, instead of specifying how many bins you have, you can specify the bin width. Okay, bin width equals 2. And here basically now my bin width is 2. Exactly what we would expect. Just a heads up, when you work with R, the argument is breaks. And when you're doing stuff in Python or Seaborn and stuff, the argument is bins. And I don't know how many times I get those confused and mixed up. And you know, I'm typing in breaks into Python and I get errors. I type in bins into R and I get errors. And so the, you know, just your brain becomes a little bit spaghetti getting these mixed up. Okay. If you want, you can specify the location of your bins themselves. Okay, so custom breakpoints here, and you get that. And notice here, I only went from 170 to 200, and so my thing just abruptly ends at 200, and so I'm missing everything off to the right of there. Okay, so that could happen also, but yeah, you have the ability to just kind of specify the bins yourself. You know, and so I think this is a fairly easy command to kind of remember as far as like setting up your bins or your bin width, as far as, you know, making these different histograms here. Okay, you can also do something called add a KDE, okay? and that will basically add like a kernel density estimate. So, your smoothed out line on top of your distribution plot. Okay, along with any of the other arguments that you want to do. You can specify kind equals KDE, and you'll just get a straight up KDE plot. All right, kernel density estimate. Kernel density estimate, basically the way you can think about it is if you gave somebody a task of, hey, draw like a smoothed out line version of the histogram, what would it look like? And there's additional arguments you can put in for the KDE. So I think here you can kind of put in your bandwidth. So the KDE smaller bandwidth will have more jagged things, and then larger bandwidth it'll be kind of more and more smooth, and you can kind of specify all of that. And it uses the SciPy Gaussian KDE there. Okay. And then another kind of plot you can do is the empirical cumulative distribution function. And so this is basically the CDF, but it's empirical. And so basically it's asking what proportion of observations in your data set have values less than, say, 170, 0, okay? And our first observation, I think our minimum length is like 172 or something. I don't know what the smallest thing is. Okay, something around there. And so if let's say we had a total of 100 observations, okay? If we had one observation, this comes up to a height of 1%. And then, as you encounter more observations, you get a little step up, right? So around 200, okay, we have maybe about 50% of our observations have values less than 200, okay? As we go further along, up to 220, it looks like maybe 82% of our observations have values less than 220. And then once we get, our max values around 230, 100% of observations, the proportion 1.0 have observations less than 230, okay? When you see sharp increases in the ECDF, that corresponds to high peaks here. And when you see kind of flattish regions right here, where the line increases slowly, that corresponds to low areas, okay? So it climbs slowly, and then it rapidly, and then slowly, and then quickly again. And so slow climb, quick climb, slow, and then I guess fairly steady out here, and then slows up. That's the ECDF. Okay, let me give you your first view quiz answer. The letter E. E as in elephant is our first view quiz answer. Oh, sorry. Okay. All right, let's look at some bivariate, multivariate plots, okay? Oh, the quiz is locked. What did I do? Week 6, Friday. Available from, oh, I put in the wrong dates. It's stupid. Okay. Okay. Me can't read the calendar. Okay. I put in May 17th, not May 10th. Okay. All right, here we go. Now, if you refresh, it should be correct. My apologies. All right, okay, so here we'll look at some of our variables. We got multiple variables, and we can do like plots together. All right, so here you can do the distribution plot. This is like kind of your bread and butter tool in Seaborn. And here we'll put in two variables. We'll put in flipper length and bill length together. Okay. Ta-da! All right, there's your plot. Okay, so you get kind of this, I don't know, heat map-ish looking thing. I don't know what you would call this thing. This is kind of your default disk. And so, darker areas mean more and lighter areas mean less. And so what we see is what? We see positive correlation, meaning we've got a bunch of penguins with flipper lengths around 190 and bill length around 35. Not a whole lot of penguins with a flipper length of 190 and bill length of 60, okay? We've got some penguins with long flippers and long bills. I don't know, flipper length 225 and bill length 50 something. Okay, but not very many penguins, or maybe zero penguins, where you have long flippers but short bills. Flipper length 225 and bill length 35 doesn't exist, right? So you kind of have this positive correlation right there, right? You can instead of having this kind of heat map, this binned, I guess this histogram with colors, you can do a KDE, and so this creates like a contour thing. Are we okay with reading like contour plots? Let's see, contour plot guide. Let me see. So the idea is it's kind of the idea, like if you had this three-dimensional thing and you just draw these stripes, okay? You draw these lines of kind of flat latitude of like the heights, and you plotted them down, this is what you get, okay? And so I guess here's another thing. So what we have here is we have kind of these two kind of rising peaks here, almost like a third peak, but this third peak is like not as sharp or steep, right? And so this is kind of the region that we see. You can do a rug plot along with the KDE, and you get all of these different little dots here. It's a little bit harder to read. You can add so that's what you have there, okay? I guess you could do a scatter plot. I think that'll be the joint plot, actually. So the joint plot, bill length and flipper length, this would be the scatter plot. And so you can kind of see how these regions here correspond to regions of, lots of dots. And this kind of third region corresponds to, yeah, not as much right there, right? Okay. And then with the joint plot, sorry, I skipped over these for the moment. I'll go back to them. With the joint plot, you also get kind of the histograms on the side. So this is a histogram for bill length, and this is the histogram for flipper length. This is basically the same histogram that that we see, up here or here, just kind of flattened it down, right? So you look at this histogram, and then I'm going to scroll down. It's the exact same histogram, just flattened down a lot. Okay, and then I think you can start to see, yeah, if this is the scatter plot, this would be the corresponding kind of kernel density estimate here. Okay, so that is the joint plot. So again, visual exploration, just to kind of look at relationships between these things, really handy, really useful. Okay, here, let me go back and do the distribution plot. And here we're going to just do flipper length. So remember, data penguin's flipper length is basically this distribution plot right here. But I'm going to do hue. Hue corresponds to the color of the dots. And we're going to link up the color of the dots, or I'm sorry, not the dots, color of the our plot with the species. We have 3 species. We have the Gentoo, chinstrap, and Adelie penguins. And so we will do that. Kind equals KDE means we're going to get smoothed out curves, and so we see, oh, okay, we got three KDE estimates for the Adelie, chinstrap, and Gentoo or Gentoo penguins here. Okay. Here, instead of kind equals KDE, I can do multiple equals stack. And so here we get the histogram. So basically this histogram, but it colors each of the bars with basically how many with the different species. Okay. If I don't specify that, let me just see what happens here. So you get kind of they overlap each other, and it's a little bit harder to read, okay, in my opinion. So basically this matches the KDE estimates, and this match each other. I don't know, maybe it's okay to read, but yeah, when you do the when you stack them, then there's no overlap, and this histogram, if you removed all the color, is exactly equal to, here, let me just go back to this histogram here. Let me just copy this. Right, so when you look at this exact shape, and that's the exact same shape as this, but here we've broken out each bar into the different species. Okay, and if you don't stack them, then they, you get shaded, and it just gets a little bit tough to read because you have the exact same count of orange and blue, and so those 2 bars ended up being kind of overlapped perfectly there. Here is the joint plot, which we showed you already. And then and with the joint plot, you can also color based on species. And so this is what you get. And so now you see, oh yeah, the 3 different kind of clusters that we saw corresponds exactly to the 3 different species, right? So you look at this and you go, huh, I wonder if there's some kind of structure there. And absolutely, yeah, this is very revealing, right? You look at flipper length and bill length and you see, yep, here's the kind of the Adelie, here's the Gentoo, and here it is for chinstrap. And we have that. And this KDE plot, right, matches exactly this KDE plot, just kind of squished down. And yeah, this density corresponds to this, right? But can I do, let me see. I don't know if I can do hue equals species. I'm not sure. It does. Oh, look at that. Ta-da. That's neat. So yeah, Seaborn makes it pretty easy to just, you try something out. I think it's one of the nice things about Seaborn is, yeah, there's kind of this little bit of intuitiveness in that you just kind of add a few arguments and it changes things up, and usually the behavior is kind of what you expect it to be. So anyway, you have that, and you have that, and it lines up nicely. Okay. So that's the joint plot. Oh, and I guess here you can just do kind equals KDE right here, and you'll get exactly that there as well. Okay. Here we can look at the iris data set. iris data set, and you can just do a pair plot. And pair plot is going to plot all four of your numeric variables and do kind of this joint joint distribution there. Okay, question. How come the graphs on the sides are different? These ones? What do you mean? These ones? I think they're the same, right? This and this. I don't know. They just color them in differently. Wait, sorry. Which ones are what are you referring to? Are you talking about the kernel density estimates? I don't know why it colors it in here and it doesn't color it in here. I'm not sure. Um, okay. Yeah, I don't know why. That's just stylistically. I wonder, there might be an argument to, there's probably something you have to dig through the documentation to say like, I want these shaded in, but I don't know. Okay. But anyway, here's pair plot, and it goes through and it plots the different values here. So the iris data set, I don't know if we've talked about the iris data set. I feel like you might have come across the iris data set. Okay. So here is you have these different, is that versicolor setosa virginica? I don't, now I'm questioning. Okay. So you got all these different, because these things look the same. Oh no, they're not. They're a little bit different. I gotta look at setosa. All right, I guess iris setosa, that's what that looks like. All right. There's apparently like um hundreds of different iris species. Is that really virginica? What is this? 17.99. What am I buying here? This is exactly described as already coming out of door. Oh, I bet you can buy the flowers. Bare root flower. Okay. Wild iris. 10 of them. 17.99. Okay, well, I'm gonna start growing my own irises here. And so this is we're looking at yeah, iris setosa, iris virginica. And then as far as the iris structure goes, okay, so or the irises, they have these things, these are called the petals, and then the little things up here, I mean, sorry, the little things up here are the petals, and then the big things that I would have called petals, those are known as the sepals, okay? And then, you know, they measured the length and the width about these things. This data was collected, I don't know, like 100 years ago, over 100 years ago. And Ronald Fisher, you know, creator of the F-test and basically all of this, one of the founders of statistics kind of did some data analysis, like linear discriminant analysis of the iris data set. And it's kind of been stuck around. It's this very kind of clean 4 numeric variables and classes there. Okay. So anyway, this is what it looks like. You can do hue equals species. So if you look at the iris data set, just do iris.head. Okay, so you get, you know, sepal length, sepal width, petal width. Again, looking at the thing, looking at the sepals, the length and the width, the petals, the length and the width. And you have these different species, Setosa, I think versicolor virginica are the different species of the iris. Okay, here are, see now these look different, right? Versicolor Setosa virginica. I am not a botanist. Versicolor Setosa virginica. Well, anyway, let's see. Everybody's got these. Oh, look, oh, Python. Oh my gosh, I don't want to load that up. Okay. Well, anyway, You can color in hue species and then the plot is beautiful. It takes a moment to load. Okay, but look at this. Look how quickly Seaborn does this. How great is that? Okay, so if you don't specify the color and you just do pair plot iris, you get histograms for each of these things. All right. And then you say, oh yeah, look at that. That's if you look at sepal length and petal length, you have a cluster here, and then these two are kind of joined. And then here, if we look at that, sepal length and petal length, we see, okay, this cluster corresponds to setosa, and then the versicolor and virginica, they are actually pretty distinguished from each other. There's not a ton of overlap, but they kind of run into each other into kind of like one big cluster if you don't color them separately. It looks like just one huge thing, but it's actually, you can see the structure of the other two, right? And so, looking just at, say, petal length, you can kind of draw a line right here between, if it's less than 2.5, it's going to be setosa. And then we would draw a line somewhere around 5, I would say, just on petal length if I had to do it. And you can kind of do it, looking at this, you see, oh, yeah, petal length right around here, high peak for setosa, for versicolor, petal length somewhere, I guess, around 5 is right around where you'd start distinguishing these things. I guess petal width could also be used right around 1.8, kind of separate them. And probably if you use a combination of both and you draw like a line right here and then a line right here, you'll get pretty good analysis, and you'll just get like a small bit of mix up right around here, maybe 2 or 4 points. Will be tough to distinguish from one another. Okay, I would say that would be the kind of the most discriminating factors to help us distinguish one species from another. But you can kind of see all of this, right? And so, data visualization is really helpful in that, like, just kind of glancing at this plot, we can figure out like, oh yeah, I probably want to use these variables or something to try to determine how we're going to distinguish between variables rather than just blindly throwing the whole data set into some kind of machine learning algorithm, which, would probably get the job done, but, having a little bit of insight and looking at the structure yourself and saying like, okay, this makes sense. That's always helpful. Okay, let me give you your second view quiz answer, which is the letter C. C as in cat. Their second view quiz answer. Okay, we have another data set. I don't know when this data set was gathered, a long time ago. All right. And it's the TIPS data set. So apparently, they went to a restaurant and then they said, how many people were in your party? 2 people. When did you eat? It was dinner time. It was on a Sunday. This was back when they had smoking and non-smoking sections in the restaurant. And I think the sex is the sex of the server. Did you have like a male or female waiter or server? And then how much was the total bill? Look at this. Dinner for 2, $8.77. You can't even get a Big Mac meal for that much. I think a Big Mac meal is like $11, $10.59 or something. I'm very sensitive to price changes at McDonald's because I probably go there too much. But anyway, so I don't know. This must have been gathered in the 90s or 2000, early 2000s or something. Okay, but anyway, this is what we have. And we measured the tip, and this is stuff we have. Okay, we can look at the information, and we have around 244 observations. Some of these are categorical variables, others are numeric. So basically these are numeric, everything else is categorical. And then as far as, the size of the party, that's an integer. Okay, we have something called a strip plot. I don't know why we call it that, but this is just going to be like a dot plot. And here we're going to put X, which day it was on the x-axis, total bill on the y-axis, that how much they spent. Okay, I guess we only got data on Thursdays, Fridays, Saturdays, and Sundays. We can add jitter. Jitter equals true. This gives us a little bit more spread. And we can see, okay, yeah, average, Saturday, is slightly skewed to the right. Okay, or I guess all of these are skewed to the right. Most bulk are down here. And then, yeah, you got some people, they decided, oh, we're going to spend $40 on dinner. These people spent $50 on dinner, which I guess back then was a big deal. That's the max, the highest amount. I don't know how many people were in that party. Maybe it was they were having a big celebration. Okay. So anyway, that's the strip plot with jitter. There's something called the swarm plot. Same kind of thing, except here it's just like random how it goes. With the swarm plot, they like avoid overlap. Okay, avoid overlap, and so you get this. I guess I don't know. I don't know if people have a strong preference for what these things are. With the swarm plot, you can also color the dots, hue. Okay. And it automatically throws in a legend, and you get, dots colored blue and yellow or gold or orange, whatever you color this is. Okay. So you get that. So same thing, just now colored in. You can color by something else. So here I'm gonna, so we've been putting day, Thursday, Friday, Saturday, Sunday along the x-axis. This time I'm gonna put sex, male or female on the x-axis, and we'll color them in by day. Same information here. This one's like way harder to read though. Okay, so now I have male, I've got female. But the colors, oh gosh, it hurts my eyes. Thursday, Friday, Saturday, Sunday, we got blue, orange, green, red. Tough to see, but now we start to see gender discrimination because look, the lowest, I don't know, distribution here, higher, and lower shifted down over here for female. So, yeah, that's revealed here, whereas perhaps that difference is not as revealed. Probably it'd be stronger just to get rid of hue. Okay. And then you can just kind of look straight at the size of these things and you go, oh yeah, you know what, this one's distribution is lower, this one is higher. Adding in the color of hue here, I don't think helps, doesn't necessarily improve the plot there. Okay. You can do it with box plots as well. Okay, so with box plots, you've got this, I mean, so honestly, box plot might be better, might make it easier to see, a little bit of the difference here. So as far as the median, a little bit different, but the third quartile on the bottom, there you see the kind of the difference there. All right, so here we have the data size there. What is this? Oh, here, box plot. Here, I put Y, the data on the Y, and total bill on the x-axis, and so this flips it sideways. Okay. And then here you can also color. Q equals sex here, right? And so you start to see some of these things. So I guess on Saturdays, not a huge difference. For whatever reason, Thursdays and Fridays, you get a bigger difference there. Okay. There's something called a violin plot. It's basically like a box plot here, except maybe like a kernel density estimate on each side. Okay, so violin plot. So basically, instead of a box plot here, it basically does a kernel density estimate and on that side and a kernel density estimate on this side. And this is the diagrams that you get. Not a huge fan of these things. I prefer box plots. Okay, you can also do facet grids. All right, so facet grids are pretty interesting. Okay, so here we're going to do a distribution plot. Okay, and then we're going to specify something called row. All right, and basically it's going to do the distribution plot, but then row equals sex. It's going to split the data into, basically sex male, sex female, as far as the penguins go, and then it will create the same plot, but for basically the different subsets of the data or facets of the data. Okay, so here I did sex equal male, all right, and we get the kernel density estimate for flipper length, okay, and then here it is for flipper length for female. And so we can see, comparing, let me zoom out a little bit. Okay, you can see there is some what they call sexual dimorphism, in that if you look at like the Gen 2 penguins, like the males have longer flippers than the females, okay? And it kind of actually is true also for the Adelie and the chinstrap penguins, right? So if you look at the distribution of flipper length for females, distribution of flipper length for males, there's a slight difference between the two, okay? The peak. So there's a lot of overlap, but we also see, oh yeah, in general, the males have longer flippers than the females for penguins. Okay. Here I did row equals sex, column equals island. Okay, so now we said, okay, looking only at male penguins on Torgerson Island, create a plot. And apparently Torgerson Island is inhabited only by Adelie penguins. They don't live, chinstrap or Gentoo penguins don't live on that island, okay? And so you can see, all right, the male and female penguins, that's what they look like. Okay, on the Biscoe Island, okay, Gentoo penguins live there, and you see the difference in flipper length for male and females, flipper length for male and females for Adelie. Apparently, Adelie penguins are on all three islands. Dream Island, and I wonder who named that. You got Adelie and chinstrap penguins, and you see the difference in flipper length. So anyway, this is basically by specifying row equals some categorical variable and column equals another categorical variable, it splits the data, and it basically just creates a plot of that subset for each of these splits or facets. Okay. You can also specify a facet grid. So here we're going to do create a facet grid, and we'll specify sex on the columns, all right? And then you do g.map, and you do the plot that you want. So here I'm going to do a histogram, and then so this will basically split the data, male on one side, female on the other side, and then we're going to get a plot here and there. Okay, the histogram plot over there and there. Okay, you can do it for, say, row, and here I'm going to do day, and then so now I'll get one row for Thursday, and then Friday, then Saturday and Sunday. Okay. You don't have to, oh, here, I mapped not a Seaborn plot, I mapped just a basic matplotlib thing, plot plt.hist, and then and it looks like this, right? And so, yeah, after using Seaborn, you go back to basic matplotlib and you're like, oh God, these things are so ugly. I mean, I shouldn't say that. Matplotlib is fine, but Seaborn certainly, I think, makes a lot of these plots nicer, in my opinion. And then, your facet grid can also have, multiple, like a thing for rows and columns. And so you can do this, and you get plot for male at lunchtime, females at lunchtime, male at dinner time, female at dinner time or something. Okay, I don't know. All right. Bar charts, they call them count plots. I don't know why, but sure, you take a categorical variable and then you get a bar chart for that. But you get the count. That's the count plot. Okay. Count plots you can also color, and you can get side by side type of things, and so you say, hey, give me the count plot for this, but color them, split it out for lunch and dinner or something. Okay, and then the last one is you can also fit little linear regression models. Now, this is just for visual exploration. This is not for linear regression analysis. So you can kind of fit a straight line. So this is total bill versus tip, and you get a line there. Okay, this line is just like fit the trend line. If you say, hey, what is the slope and intercept? It is not possible with Seaborn to extract the slope and intercept from the plot. And that was a design choice of the people who created Seaborn. They said, you know what, I don't want you to use Seaborn to do your analysis and figure out the slope and the intercept and residuals and stuff. This is just for visual exploration. So sure, if you want to fit a trend line and just try to get an idea of what that looks like, we'll allow you to fit the trend line, but we're not going to let you extract out the slope and intercept. So that was kind of the philosophy behind Seaborn as far as for data visualization and exploration there. Okay. Here you can rather than fitting just a linear regression line, you can fit a low-S curve. Low-S is locally weighted scatter plot smoothing, I think is what it stands for. And basically it tries to fit a smoothed out line. This is not the best data set to illustrate low-S, but you can have like curved lines and stuff if needed. Let's see. You can get a residual plot. Okay. Again, this is just to kind of see if like linear regression is even appropriate in the first place. But again, it's not going to give you further detail or analysis here. And so you see this and go, is it? The residual is constant throughout. Not quite, but maybe it's okay. All right. Here we're going to look at tips versus smoking habit. Smoker yes, smoker no, and it seems like the non-smokers tip at a greater rate. I don't know. Well, anyway, it's hard to see, but they do have different slopes based on that. But anyway, these are just kind of basic things. I've just touched upon some of the basics in Seaborn. You're going to find a lot more stuff at the Seaborn documentation. What I like to do is I like to just go to the gallery, okay? The Seaborn gallery and go, oh, that looks cool. All right, and how do I do that, right? Or, you can kind of look at some of these different things and you get an idea of like, oh yeah, oh, what is this, right? And you can look at the corresponding code. So, so that's, I think, pretty good. And then the full documentation under the API. API reference is going to have your full documentation there. Okay, let me give you your last view quiz answer. The letter B. B as in bear. Okay, we will end here for today. And have a good weekend. And we'll see you Monday. Maybe in person, maybe online. We'll see what happens. All right. Have a good weekend.